Now we move on to dimensionality reduction. Please, if you have any question, you may ask. Before we keep going, then later you feel lost inside the class. Dimensionality reduction sounds similar to feature subset selection, where you try to reduce the number of features, but actually the mechanism is totally different. So in feature subset selection, we take fewer features. We reduce the number of features by dropping some and maintain others. While dimensionality reduction is totally different. So dimensionality reduction refers to the process of reducing the number of input features, how, in the data set, while preserving the key information inside the features, while preserving the key information, the variation. How now we talk about how it works. It works by generating new components. Instead of features, we say components. Components, like component 1, component 2, component 3, that are combination of original features. These new features are often referred as principal components or latent variables. As if you take, let's say you have 10 features, you squeeze all of them, and you get as a result 6 features. This is dimensionality reduction. Earlier, feature subset selection, no. You select some and drop some others. You drop others. In dimensionality reduction, no. You apply some process to take the key information, the essence. You squeeze them in order to get the key information from all features while representing all of them in fewer number of features. The process is totally different. Okay? You understood the concept, just you need to understand the different mechanism. They're not eventually, you're not saying I took only 5 features and I dropped 5. No. You created a new components, or what we call them latent variables. Okay, let's say I have median income. To make it easier for you to understand. Median income. What else we have? Total rooms. Okay, total bedrooms. One more. House price. This is the target, so we're not going to touch. How about longitude and latitude? We had, let's say, longitude and latitude. Okay, now if you are applying feature subset selection, you come and say, okay, I'm going only to take median income and let's say total bedrooms. This is a feature subset selection. You select some and drop others. Now, if you are applying dimensionality reduction, like principal component analysis, or stands for PCA, we take all the 5, we squeeze them, and then instead of getting this feature, we get what's called component 1, component 2. Let's say I'm interested only to get them squeezed into 2 components, 2 features. So component 1 and component 2 are the result of combining all the 5 features together in a process done by under principal component analysis. So what is component 1? We don't know. Is it median income? We don't know. Is it total rooms? We don't know. You got the idea? Different. Like you have squeezed 5 different fruits, and then you come up with a cup of juice, 1 component, cup of juice. Then can we say this is fruit 1? No, this is squeeze of all 5 fruits, right? So we don't know. We cannot say this is only fruit 1. You got the idea? So this is the difference between PCA, for example, as one of the dimensionality reduction, comparing to feature subset selection. So principal component analysis is widely technique used for dimensionality reduction and feature extraction in data analysis and machine learning. The goal is to transform high dimensional data set to lower dimension space while retaining, you see why it's highlighted, while retaining as much of information in the original data as possible, like the juice cup you got as a result of squeezing all the features. So you retain all the information from all. into one new component, or we call it latent variables. So PCA works by identifying what's called principal component of the data, which are direction of maximum variation in the data. These principal components are orthogonal to each other and are ranked in order of their explained variance, with the first component explaining the most variance. So meaning, what does this mean? When you apply PCA, let's say you got component 1 and component 2. Component 1 will have the major information that he got after squeezing, let's say, the 5 features. Component 1, let's say, will contain 90% of the information from the 5 features. Component 2 may be only 10% or 5%. Understood? That's why it says here, with the first component explaining the most variance in the data, followed by the second, third, and so on. Okay? Any question? Limway, question? No. Sorry, what was your name? I keep forgetting. Kaizen. Yes. Kaizen, okay. Any question, Kaizen? Is it clear? There is mathematical equations behind this, but I'm not going to explain. Just I need you to understand the concept. So when we get component 1, can we say this is median income? No, we cannot say that because they are a sense of all together, combined. Okay? So remember this example. So this will actually help you to understand the difference between feature subset selection and principal component analysis. Let's look into this example. This is an interesting example. Again. So let's look into this example for principal component analysis. Let's say we have collected data for the average consumption of 17 types of food gram per person per week for every country in the UK. UK is a combination of 4 countries. Here we cannot see the rest. There's another country, England, North Ireland, Scotland, and Wales, right? Wales, I think. Yeah, so there are 4 countries. And here are the 17 attributes. By the way, don't be confused. Here, the features are the food consumption. So how many features we have? We have 17 attributes. How many records we have? We have 4. Just you need to rotate the data set. So we have 4 records. For each country has 1 record. The food consumption, the average of food consumption per person per week. And let's say we are interested to find out the overall difference, to describe the overall difference. Can you just by spotting these 3 countries, there's the 4th one, not here, but still the data here you can see. Can you tell which country is quite different than the others just by looking into this one? Quite difficult, right? So we're going to apply principal component analysis to squeeze all these 17 features into 1 feature, 1 component. Then we can actually see the difference quite clear between one of those 4 countries. Clear? So let's find out. If we apply taking only the first principal component, so that means from 17 attributes down to 1 component. And then if we draw 1 component, we're gonna get just simply a line figure. We draw the lines. Now, obviously, immediately we can spot North Ireland is quite different than the others, right? So North Ireland is quite different than Wales, England, and Scotland by applying principal component analysis. Why? Because each one value of those has actually retained the key information from the 17 food attributes. So immediately we can see North Ireland is different as overall difference with the other three countries. Same, how about if we take two components? So this is PC1, that means principal component 1, and PC2, principal component 2. Then again, North Ireland is different than the others. So we can conclude by applying principal component. You see, we're not taking feature selection. We're squeezing all the 17 attributes into only two components. Then immediately we see North Ireland is quite different. So this is an interesting example showing you before and after. Any question? You can do the same. If you collect about Malaysia, let's say food consumption, then apply principal component analysis, draw the figure. You can see which state or which city has quite different consumption behavior than the others. Okay. Curse of dimensionality. What we mean by curse of dimensionality, where we have too many attributes inside the data set. Having too many attributes not necessarily can be a good thing. Not necessarily can be a good thing. Can be a curse if these attributes actually cause to increase sparse data. What do we mean by sparse data? That means you have a lot of data with zero value. So let's say you have a lot of values, attributes 1, let's say attribute 1, attribute 2, until attribute 100, attribute 101. But if you check the data, you find 0, 0, 0, 0. Maybe another attribute here, 102 is 1. The second record maybe here is also 1, 0, 0, 0, 0. So there's not much information inside the data. This is we call sparse data. Sparse data. That means you have data, correct, but it fills with 0. So 0 doesn't give you much information, like in this case. Okay? So sometimes having too many dimensionality inside the data set can cause this data to be sparse. Okay? So this is what we mean by curse of dimensionality. The curse of dimensionality is a phenomena that occurs when working with high dimension data. That means you have too many attributes inside the data, where the number of dimension features in the data is much larger than the number of samples. Let's say you have 100 samples only inside your data set versus 500 features. Okay? So this can actually cause having sparse data. And why we care about curse of dimensionality? Because it's actually difficult to distinguish meaningful pattern when you have sparse data, because there's no information, 0. Okay? So it's very difficult to distinguish meaningful patterns. So many problems occur when you have high dimensional vector or are generally very sparse. That means have a lot of 0, and this can increase the risk of overfitting. What we mean by overfitting? Anyone knows from another course attended? Overfitting is one of the challenge. I think we already explained or not yet. Overfitting, the main challenge. Overfitting simply means when the model tries to memorize the data rather than finding the patterns. You know the snake game? You play the snake game? Yeah, exactly. When the model becomes like the snake game, try to cross as many data points inside the data set, the model becomes overfit. That means the model is trying to memorize the location of the data points. Okay? Anyway, we're going to discuss further about overfitting and underfitting. Okay, so what are the motivation behind dimensionality reduction? When we are interested to apply dimensionality reduction, one reason to speed up subsequent training algorithms. We have too many data and we would like to reduce the dimension of the data. To visualize the data and gain insight, like now the example we've seen for the 17 food type of UK, right? So actually we visualize the data and we gain insight that North Ireland or Scotland was quite different than the others. Reduce the noise also can be reduced by applying dimensionality reduction, reduce the noise inside your data, enhance interpretability, making it easier to understand maybe the relationship inside your data, like the example now we've seen, where we saw that one country is quite different than the others, or to save space. Save space because simply you are compressing the data. And instead of having too many features, now you have fewer number of attributes inside your data set. And another interesting reason behind dimensionality reduction for security reason, to disguise the data, the original data. Let's say I collected data about this class, about age, let's say favorite food, favorite drink, and so on and so forth. Okay? And I would like to secure the data. If somebody looked at the data, he won't understand. Then I can apply dimensionality reduction, PCA, component analysis. Let's say I collected 10 features, 10 questions for each one of you. Then I make them maybe into, keep them 10 or maybe reduce them to 9, still containing the key information, but the data no more understandable. What is feature 1? Nobody knows. Feature 2, what is it about? Nobody knows. Just we know this is component 1, component 2, component 3. Okay? However, there's drawback when we apply dimensionality reduction. Some information are lost. So PCA retain as much information as possible, but doesn't retain all the information. Okay, so some information are lost. There's possibility of degrading the performance of next algorithm. Can be computationally intensive. Why? Because we are including some more process. And instead of just going straight forward to the training model, now we are increasing some process by doing dimensionality reduction. So it becomes computationally intensive. We are adding complexity to the pipeline. So later we're going to see when we prepare in data preparation, we create pipeline. So that means inside the pipeline, there are small processes, let's say replacing missing value, looking for outliers, and so on and so forth. Now we also include inside the pipeline another process for dimensionality reduction. So the complexity of the pipeline is increasing. Transformed features are hard to interpret because eventually you will get component 1, component 2, component 3. You don't know what these are to interpret your results. So according to your textbook, as a tip, it's best to try training your model with the original data first before deciding to use dimensionality reduction. Just use your data. No need to use dimensionality reduction. Although there are situations where reducing dimensionality of the training data may help improve the performance by filtering out the noise and unnecessary details, in most cases, it will only speed up the training process and not result in any better performance. As a tip. So not necessarily this is going to enhance the performance or maybe help you to reduce the noise inside your data. Okay? Any question? Today, good, no talking. Well, that's good enhancement. The performance is higher. Feature subset selection is working. How to apply principal component analysis. Also, you can use sklearn, scikit-learn, decomposition. You import the class called PCA. Then you can specify the number of components. So let's say number of components 2. That means I want to reduce the number of dimensions inside my data set, let's say from 17 down to 2. Then you call fit and transform.